Hey, welcome back to chapter 6. So we're going to take a look at chapter 6 today. And in chapter 6, we're going to be discussing something called the normal probability distributions or normal curve distributions, probability distributions using the normal curve. Lots of different ways to say it, but we're looking at this idea of taking what we did last chapter with our discrete probability distributions, which were those guys where we had an x and a p of x, and x had to be like 0, 1, 2, 3, or something like that. And then p of x's were probabilities that added up to 1. We're going to take that idea, we're going to say, hey, wait a second. What if we have a scenario, a situation where our random variable can be anything, can be continuous? And so that's where we're going to start today. All right, so we're going to start with some key concepts that we're going to take a look at. Key concepts in this section is going to be something called the standard normal distribution, which is one specific type of one specific normal distribution that has a mean of 0 and a standard deviation of 1. Okay? And then we're going to use that curve, we're going to use that standard normal distribution to find areas, which we're going to interpret as probabilities or relative frequencies, to correspond to regions under the graph. And that'll make a lot more sense here in a minute. All right, so we're going to start with a super simple example. Okay. Now, like I said earlier, in the last chapter, we had discrete probability distributions. In this chapter, we are going to have continuous probability distributions. We are going to have scenarios where we have a continuous random variable. Now, if my random variable is continuous, meaning it can take on any value in a range, how do I calculate probabilities for that random variable? And so what has been decided is that rather than having a probability distribution, we are going to have a function, algebra, some sort of algebraic expression that is going to be used to calculate probability. So someone is going to hand us algebra. We're going to graph that algebra. That algebra right there, that f of x, whatever that algebra is going to be our probability function. And then we're going to have a range of values, an a and b, and then that horizontal range there from a to b, that is going to represent all of the values for our random variable. And then someone's going to come to you and say, what's the probability that it's from here, some x sub 1, to here, some x sub 2? And you're going to say, okay, I can do that. I just need to measure, to calculate the area that is under that curve from x sub 1 to x sub 2. When I find that area will give me then the probability that the random variable is between some x sub 1 and x sub 2. All right, so the properties that are going to be required for these distributions are going to be that the area under the curve, the area under the graph, has to add up to 1. So from somewhere to somewhere, from some a starting value to some b ending value, the total area under the curve must be 1. Okay. Now, the first example we're going to look at is going to be the uniform distribution. And the uniform distribution goes one step further and says, what if our probability was always the same? That is, what if our function, our f of x, our probability function, was a horizontal line? And if I said, okay, it's going to start at 2, it's going to stop at 5, and I know that the height of it has to be exactly 1/3, because the rule for probability distribution says that this entire area must add up to 1, and if that area must be 1, And I know from geometry that that's a rectangle. And so area is length times width. If this side has a length of 3, then the height would have to be 1/3 to get an area of 1. And then someone could come to me and say something like this. What's the probability that 2.5 is less than or equal to x is less than or equal to 3.2? And I would say, okay, I'm going to find 2.5. There's 2.5 exactly. There's 3.2 exactly. What's the area of that piece right there? And the area of that little blue piece would then be our probability for the range of values 2.5 to 3.2. Now, the way we'd find that is we'd find the area of that rectangle. It has a height of 1/3. It has a width of 3.2 minus 2.5. 3.2 minus 2.5, what is that? 0.7? Let me grab my calculator because my brain's not quite working. So 3.2 minus 2.5, I get 0.7. Yeah, I was right. And so I've got 1/3 times 7/10 or 7/30. And then I could represent that as a percent or a decimal or whatever. And that would be the probability that whatever this random variable is measuring would fall between 2.5 and 3.2. Okay? So that's what we're going to be doing for all of chapter 6, is we're going to continue to calculate probabilities, but our probabilities are going to be measured in a different way. Instead of having just a table of values where when it's 1, the probability is this, when it's 2, the probability is this, someone is going to hand us algebra. That algebra is going to give us a function that we are going to use to calculate probabilities. Then they're going to give us ranges of values and say, what's the value, what's the probability for this range, for that range, for the other range. Every single time, it's always just going to be about measuring area under a probability density function. Okay? So the fancy name for this guy is a probability density function. Okay? All right. So our density curve or our density function is whatever the algebra is that satisfies those two requirements. One is that the area must be 0, add up to 1, and then 2 is that it can never be negative. Okay? All right, so let's take a look at our first example here. During certain times at JFK Airport in New York City, passengers arriving at a security checkpoint have waiting times that are uniformly distributed. All right, I want to stop right there and point out something. This phrase right here, uniformly distributed, means something. Right? To say that the wait times are uniformly distributed means that their probabilities are evenly distributed over the entire range of values. So when they tell us that it's uniformly distributed between 0 and 5 minutes, it tells me that my x, my random variable, is valid from 0 to 5, and that the probabilities for all of those are always the same for any range of values in there. Right? Now, when we take a look at the math that's going on here, the top edge of this curve, our probability density function, it's a horizontal line at 1/5, which is the 0.2 you see over there on the y-axis. Now, how did they get that? Well, the rule says that since the area must be 1 and its width is 5, then its height must be 1/5. So that when we multiply them together, we get an area of 1. Okay, so how does this work? Well, in the problem, when we're told we're universally distributed, we're going to be given an A and a B. That A and that B are going to tell us where this thing starts and where this thing stops. And our probability density function is always going to be 1 divided by B minus A. So for this problem, since they told us that A was 0, and they told us that B was 5, then our probability density function, our density curve, is 1 divided by 5 minus 0, or 1/5. Okay? Depending on how this information is given to you, sometimes the formula is really, really necessary. And sometimes it isn't. Sometimes you can just look at it and go, oh, that's 5, so this has to be 1/5, and I'm done. But let's just make up some random scenario. What if they told you A was 1.2 and B was 6.3? I can't look at those values and tell you what F is. I'd actually have to use the formula and say that for that scenario, it would be whatever 6.3 minus 1.2 is, and I'd have to do the math there. Okay. So there's a formula for it, and we like the formula. The formula is good. The formula has purpose. We try to use the formula when it's appropriate to use the formula, but if there's a shortcut, if the A and B are easy, we go with them. All right. So when I'm looking at this uniform scenario, I'm recognizing some behavior, some truths, I guess we'll say, about the probabilities. One is that all different possible waiting times are equally likely. That since the probability down here and the probability up here is the same, that the chance of waiting just a short wait, 0 to 1 to 2 minutes, is the same as 3 to 4 to 5. Okay? And that if I had an accurate enough watch, that any possible waiting time could happen. 1.2, 4, 5, 6, 7 minutes could happen if I had an accurate enough watch. Okay? And that right there, this thing, is what makes this a continuous probability function. That x could be any value, and there are no restrictions as long as it's something just between 0 and 5. All right, so given this information, our first example for working a problem is we're supposed to find the probability the randomly selected passenger has a wait time of at least 2 minutes. So the first thing I'm going to do is I'm going to turn that statement into a probability statement. I'm going to find the probability that x at least greater than or equal to 2. Now, in terms of our problem, what that really means is this. Now, while the exact example here, while these words written right here never mention 5, I know that my model, my math, is only good between 0 and 5. So to say bigger than 2 really means to say from 2 to 5, because there is that cap at 5. Okay? And so how do I find that? Well, I just find the area. So I'm going to take the height, which we said was 1/5 or 0.2, and multiply it by the width. Oops. I almost wrote equals to. Times 3, which gives me 3/5, 0.6, 60%, depending on how you like to represent that. And then I would say that if you randomly selected a passenger, they have a 60% chance, the probability is 60%, that they would have a wait time of at least 2 minutes. Okay? Now, where did all this come from? Well, this came from my probability density function. And these guys are right there in the problem. All right, so normal distributions are something different, but this is a uniform distribution. Uniform distributions are when the probability density function is a constant. There's a formula for finding it. Okay? A and B will be given somewhere in the problem. They have to be. You have to be told where it's valid. And from A and B, you can find the algebra for that horizontal line. Okay. Now, what if things get more complicated? What if instead of a flat horizontal right here, what if this thing wiggled? What if they had blah, 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 blah? Well, we'd have to have algebra for that. Now, there is no restriction as to what that algebra could be. We, in this course, are going to restrict ourselves, though. And we're going to look at a lot of these guys. We're going to look at a lot of things called normal distributions. Now, a normal distribution is when you have a continuous random variable that follows this algebra for its probabilities. Now, I know what you're thinking. You're looking at that and going, holy cow, that is a hot mess. Yes, yes, it is. You know some of these things, right? Mu, that's our mean, right? Sigma, that's our standard deviation. Right? Pi, that's that 3.14159 number, da 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 da. E, 2.71828, da da da, kind of like pi. It's a transcendental number that goes on forever. And then if you put all those numbers into this formula, you get something that looks like this. You get this bell-shaped symmetric curve. Now, I don't know what courses you've taken in math before this, so I'm going to toss some phrases in here that may or may not make sense, but hopefully they will for most people. It's increasing on this half because it goes up. It's decreasing on this half because it goes down. It's concave up over here and over here. It's concave down here in the middle. But the biggest thing you have to remember about this is when you are working with a normal distribution, that red algebra around that outside is our math that we're going to use to find probabilities. Okay. Hopefully, this behavior over here and over here makes sense to you. This curve has a horizontal asymptote, meaning that as the independent variable, that's the horizontal axis, as it gets bigger and bigger and bigger, that curve just keeps getting closer and closer and closer and closer, but never quite gets to the horizontal axis. It gets really, really, really close, but never quite touches it on both ends. Okay? Now, that's both a problem and a non-issue. Right? The problem is, if this thing is measuring probability, then the area under here has to equal 1. And if this curve never touches the axis and never stops, how do I measure the area? Well, luckily, we don't have to worry about that in this course. That's a complicated mathematical problem that you would deal with if you took a calculus course. For us, we're just going to use technology for the most part to find these values. And we're going to say, hey, I agree that this thing goes on forever, but realistically at some point out here, at some value out here somewhere, it's going to get so close to that horizontal axis that everything after it is going to be so small that I kind of just don't care about it, because it becomes such a small amount that it's out there in that 4th or 5th decimal place where the rounding is going to make it go away anyway. So here's where we're at. We're in the probability section. Someone is going to hand us information about a continuous random variable that can be modeled by a normal distribution. We're going to do this. We're going to make this curve right here, and then they're going to say, hey, find the probability from here, some x sub 1, to here, some x sub 2, and we're going to measure this area right here. Now, the challenge that we have with measuring that area is geometry has failed us. In the previous example with the uniform distribution, it was just a rectangle, and a rectangle, length times width, we're done. Here, I can't use a rectangle to measure this because the top's not flat. So this becomes a very complicated problem. Again, not going to be an issue for us, as we're going to let somebody else do the complicated work. We're just going to figure things out. Okay? So this region in here is going to be the probability that x sub 1 is less than our random variable, and x sub 2 is the upper end. We just find that probability. Okay? All right. The way that we're going to work this is we're going to take a little trip down memory lane, do things historically first, and then show you the modern technology. Right? Historically, we would convert everything to what's referred to as the standard normal distribution. Now, and the work we're going to do in the most of the rest of this session is going to be standard normal stuff. Okay. The standard normal distribution is a normal distribution where the mean is 0 and the standard deviation is 1. The mean does not have to be 0. The standard deviation does not have to be 1 to be a normal distribution. But as soon as I see this modifier standard on there, I know that I'm dealing with the normal distribution where the mean is 0 and the standard deviation is 1. If those were any other values, it would not be a standard normal distribution. Right. The area under the density curve is always equal to 1, so that's not a big deal. To tell the world that we're working with a standard normal, we identify the horizontal axis as z. And we do this to distinguish this as the standard normal distribution. So if you just saw some curve out there and they call this x, you're like, that's not a standard normal. But if you saw a curve out there and they call this z, then you'd be like, oh, that's the standard normal. That means the mean must be 0. The standard deviation is 1. With the other guy up here, the mean could be, I don't know anything. And the standard deviation could be, again, I don't know anything, right? So we're going to start by looking at a special case, the standard normal distribution, which has a mean of 0 and a standard deviation of 1. We label the horizontal axis as a z to make the world know this is what we're dealing with here. Right? We're going to find areas and the associated probabilities using either technology or a table. I'll show you both ways. Technology is strongly recommended. Right? We recommend technology because it gives a more accurate result, and it's also faster. Okay? All right, so I will show you how this works the old way with tables first, and then we'll go to technology, and then we'll end this video there and start up a next video. All right, so here are the ways that probability used to be found using the old way. This is looking things up in books and tables of values. Right? Before technology made this an easy problem, this is how we had to do it. It was just brutal. Right? So if someone would hand you a standard normal distribution, they would give you a z-score, and they would ask you to find an area. Now, there are 3 problems that are ever asked. There's this problem right here, which we refer to as a left tail problem, because we are given an upper limit of negative 0.24, and we're asked to find everything left of that. Their other 2 versions of this problem are the right tail version, and in the right tail version, you'll be given a value and asked to find everything to the right of that. So this would be the right tail version. And then the third version of this problem is where you are given a lower and an upper and asked to find a strip in the middle. So they'll give you a lower value, they'll give you an upper value, and ask you to find a piece in the middle. Right? Now, technically, there's a 4th version where you do a left and a right tail, but it's just combining 2 different versions, so I'm not too worried about that. Right? All right, so we're going to focus on just the left tail version using a table of values. Right? I already know the area is 0.4052, and that's going to help me make sure I get the right answer. So if someone handed me this problem and said, hey, do this math, find the cumulative area for a z-score of negative 0.24, meaning find that blue area right there, I would go to my book, I'd open up my table. Honestly, these things used to be books. You used to keep a book on your shelf of all the areas for normal distributions. And you'd look up in the book your z-score. Now, the way the books worked is they had a left-hand column over here that represented the 1s and the 10ths digits for your z's. And then they had other columns that represented the 100ths digit for your z's. Now, because of this, most problems are always going to have a z-score to 2 decimal places. And then what you'll do is you'll find the row and the column that make your z-score. So since we're looking for negative 0.24, we got the negative 0.2 row and the 0.04 column, and where they intersect down there at that 4052 would give us our area. Now, in some of the homework problems, they're going to give you the option of clicking on the table to look these things up. Please don't do that. There's no reason to, there's no advantage to doing it that way. All it's going to do is add extra work. Okay? But this is how we used to do everything. You would have one half of your book that would be left tails. You would have one half of your book that would be right tails. And then you'd use those two to figure everything out. Right? So the homework is going to reference this table A2. Right? Now, the A2 table that it references is for z-scores only for standard normal distributions, which means you have to have a mean of 0 and a standard deviation is 1. Right? The table is split up into 2 pages. The left page is for negative z-scores, the right page is for positive z-scores, and every value in the body of the table is a cumulative area from the left. So the table that they have in the homework is only left tails. Right? Please don't use it. I'm showing you how it worked. I'm showing you how it was used back in the day. Please don't use it. It's so much faster to use technology. And let me show you what I mean. I'm going to bring up my calculator, and I'm going to go ahead and calculate that problem we were just looking at. If I want to find this area for this z-score, I'm going to go to my distribution menu, and I'm going to go to my normal CDF, my normal cumulative distribution function. Here's the one thing where we have to kind of muck around with it. Whoever programmed this wanted you to have both a lower limit and an upper limit. Technically, there's no lower limit on this problem because it goes on forever to the left. So we're just going to put in a large negative number. Negative 10,000 sounds good. We're going to put in an upper limit. Negative 0.24, that's our upper limit. Our mean is 0 and our standard deviation is 1. We know that because it told us in the problem that we were working with a standard normal distribution. I'm going to paste that back in, and I get my 40516 rounded to 4 decimal places, 4052. That's the way we should do every single one of these problems. There is no reason to look anything up in the table. Tables have no purpose. In today's statistics, everything should be done using technology. I'm going to end this video here, and we'll come back and we'll start the second video doing a bunch more examples on how to do right tails and strips in the middle and all that. All right. See you for part 2.